Alrighty, seeing. Just waiting for this to go live. Alrighty, looks like we're live. Alright, so welcome back everyone to another stream. Alright, so up until this point, we've been focusing specifically on the hardware of our ROS2 robot. We've taken it's sitting over there at the moment, but we've taken a differential drive chassis that I've had for a while. We've built a logic board, microcontroller logic board, to drive the motors and to hold a Raspberry Pi Pico 2. It then two brushless motors connect to it that have integrated controllers. So realistically, it's just it's 3 pins, PWM, direction, encoder input. It's got an IMU, and it's got a simple little low side driver circuit to control the motor on an XV11 LiDAR, and then it has the header to connect the XV11 LiDAR. It also has a single servo header to control a tilt servo for the camera, although we didn't end up integrating the tilt servo into the robot. So, today we're hopefully going to be finally checking out ROS2 for the first time. So this can be maybe a little different or hopefully maybe slightly different than some other ROS2 kind of tutorials. So what we're specifically going to try to do is, run-of-the-mill, we're going to get a Ubuntu 2404 image set up for the Raspberry Pi, because ROS is highly coupled to Ubuntu. In a lot more ways than other Linux software typically is coupled to a distro. It's really coupled to Ubuntu. It's a pain to run ROS on anything that isn't Ubuntu. Even other Linuxes. Continuing off of that, I don't run Ubuntu on my desktop, and I'm not going to try to distro evangelize to anybody right now, but I don't run Ubuntu. So we're going to try to do all of the ROS tutorials, or at least some of the ROS tutorials, using ROS2 in Docker, because we can use a Ubuntu 2404 image in Docker running on whatever host Linux you want to use. So let's see. Right. So kind of the idea for today is that we're going to start with getting an image installed on the Raspberry Pi and have it start coming up. And then we're going to do a direct ROS2 installation on the Pi, and then we're going to kind of mess around with running ROS2 in Docker on my desktop here. And hopefully what we can get to is, I personally have not written any ROS2 software before. So what we're going to be checking out mainly is there is this framework called LinoRobot, LinoRobot 2 specifically, which is a really handy helper. Basically, it's a bunch of predefined packages to help build ROS2 robots specifically surrounding the Nav2 framework, which is what we want to do, because the Nav2 provides SLAM. So there's a couple of things that we're going to have to do for this, or it also handles running the robot in a virtual environment, virtualizing the robot. So kind of the main parts of this are, there's a bunch of bring up tools, scripts, that and the other. We will basically have to provide it a model of our robot. We'll have to provide it all the parameters that define kind of how our robot behaves. And then it'll also bring up the hardware that runs the microcontroller that actually bridges ROS2 to hardware in the robot. So we're not actually going to be directly using the upstream LinoRobot, because the upstream LinoRobot package assumes that you're using a Teensy microcontroller, which is a really powerful microcontroller. Let's be honest, it's a 600 megahertz. Teensy 4 is a 600 megahertz Cortex M7 based platform. It's really fast. Don't get me wrong. It's super scalar. 600 megahertz microcontroller. It's almost 2 instructions per clock cycle throughput at 600 megahertz. Compared to our little dinky Pi Pico. which, I mean, at least we have 2 cores, but we're at 150 megahertz on 2 cores. So like where the Teensy has still probably got at least another 50% performance on us. But anyway, we're not doing a whole ton on the microcontroller. We already have way more power than we need. So we're going to be looking at basically this fork of Lino Robot 2 by a user called Hippo5329. They've implemented support for other microcontrollers, namely ESP32 and PiPico. They also support running things over Wi-Fi, but we're not going to do that. We've got a direct USB connection to the Pi. So kind of our goal for today is to try to go through some of these ROS2 tutorials so that we can learn at least the beginner ones, just so we can at least get through like how workspaces work, packages work, some simple service type stuff, just so we can at least understand, hopefully so we can understand enough to start working on the microcontroller code. And without further ado, let's start setting up the Ubuntu image for the Raspberry Pi. So I have a 128 gigabyte micro SD card plugged into my desktop. So we're going to use the Raspberry Pi imager to create an image. And you may ask why I don't just download the image off of Ubuntu's website and use DD to write it out to the micro SD card. And realistically, that would be perfectly fine. But what I really like about this imager tool is that you can pre-configure users and services and, let's say, the Wi-Fi network. So I don't have to go plug a screen or an Ethernet cable or something into the Raspberry Pi to start getting it ready to go. I can literally just go and say, I want a Ubuntu, or wait, what is Raspberry Pi OS? Oh, that's still Raspberry Pi OS. So yeah, other general purpose OS, Ubuntu. We want 2404 LTS. We want the server version, just because we're running headless. So Ubuntu server 2404. We're going to use this SD card. We're going to go next. We would like to apply OS customizations. And what we're going to do is we're going to set the host name to, because I said that this chassis is called a Stinger. That's the Robotics Connection Stinger was the chassis built on. So we'll just call the host name Stinger. We'll set a username and password. And we'll just set this to something stupid like robots. Actually, let me type in a different password. I'm going to put this off screen so y'all can't see. All right. And then we can configure a wireless network. And I'll do that because that's my network. And then I will type in the password over here. All right. I'm in the US, so we'll use the US Wi-Fi country code. We're going to be way down here. US. All right, set locale. Pacific time zone, which is America, Los Angeles. Keyboard layout US. Save. Actually, edit settings still. Services. We want to enable SSH by default. We're going to copy my my SSH public key, which is not a secret, so I don't know why I hid it over here. But anyway, we got that. Allow public key only. This could be our key. Other options, play sound when finished, eject media, enable telemetry. We would disable telemetry. I mean, I don't really care too much about what Ubuntu's skimming off of my robot here, but I don't really want to, well, whatever. So we got that, enable SSH, use my public key so I can sign in with my SSH key. Stinger, all right, save, and it should connect to, yes. All data will be erased. Yes. All right. And then I need to authorize writing to that. All right. So we'll get our Raspberry Pi configuration here shortly. And anyway, the battery is still charging in the other room, so we can't quite turn on the robot yet. Anyway, so while we're waiting on that, let's start looking at some of these ROS tutorials. So we're, as I said, like this gonna be doing it on my desktop just for now. But we're going to try to do it through Docker, and so I guess the prerequisite here is to have the Docker runtime running, right? So I do have the Docker runtime up. You can see some of my old experiments in here. So we're just going to, okay. We're gonna, okay. This says, Docker pull OSRF ROS Humble Desktop. What we're going to be using a version of ROS called Jazzy, or ROS2. Oops, sorry, ROS2 Jazzy. So the current version of ROS2 is Kilted Kaiju, but that the way that ROS, kind of like Ubuntu, they have a major release every year. Well, I mean, Ubuntu is a major release twice a year, but every year ROS has a major release in May, I believe, and they only every other year's release is considered a long-term support. So Kilted Kaiju is the current version of ROS, but it will be unsupported in May of next year, and replaced with whatever next year's release is. However, Jazzy is the current ROS2 LTS. It came out last year, and it will. I don't know what their official support, but I mean the fact that you can still do ROS2 Humble means that it'll probably be a couple of years. So anyway, we're going to focus on using Jazzy. And so what we'll do a Docker pull OSRF ROS. This is a community contributed guide here. It's under the ROS2. Okay, well, we'll actually switch to Jazzy here and see if this shows up. Hey, there is a version of this guide for Jazzy. Okay, so docs.ros.org, English, Jazzy, how to run 2 nodes. Okay, we don't actually, we're just, whatever. Okay, so we're going to copy this. And I think there's also might be a full. Okay, yeah, so full has all of the visualization tools like RViz, which is the visualization software. So we're going to use ROS Jazzy Desktop full. There's a lot of stuff that it's downloading here. Alrighty. So while this is downloading, so basically let's start by looking at configuring the environment. This is actually going to be pre-done for us, I believe, by the Docker containers set up or pre-configured environment here. So we'll just verify that this stuff is valid here. So we'll go back here, Docker run interactive TTY Jazzy Desktop full, and it should give us a prompt. Hey, look at that. And if maybe we can do ROS2 help. Does that work? Hey, it does add the ROS2 tools to our path automatically. All right, let's see. Ubuntu server has been written to generic mass SD card. You can now remove the SD card from the reader. All right. So we'll close that. We'll pull up another terminal here. We'll run sync, which means that I have everything flushed. We'll pull the SD card. We'll just leave this sitting here for now because the battery's not done charging. All right. So what this would have us do anyway, so flipping back to the configuring the environment tutorial, right? ROS2 relies on the notion of combining workspaces using the shell environment. Workspace in ROS is a term for the location on your system where you're developing with ROS2. The core ROS2 workspace is called the underlay. Subsequent local workspaces are called overlays. When developing with ROS2, you will typically have several workspaces active concurrently. Combining workspaces makes developing against different versions of ROS2 or against different sets of packages easier. It also allows the installation of several ROS2 distributions or distros such as Dashing or Eloquent or Humble or Jazzy or Kilted on the same computer and switching between them. This is accomplished by sourcing setup files every time you open a new shell, or by adding the source command to your shell startup script once. Without sourcing the setup files, you won't be able to access ROS2 commands or find or use ROS2 packages. In other words, you won't be able to use ROS2. Prerequisites. Before starting these tutorials, install ROS2 by following the guides on the ROS2 installation page, which we will need to go do once we power up the Raspberry Pi. These commands in the tutorial assume that you installed the following The commands used in this tutorial assumed you follow the binary packages installation guide for your operating system, Debian packages for Linux. Again, another Ubuntuism. I mean, I know Debian packages, Deb packages are Debian packages, and Debian's a distro, but Ubuntu's built on Debian and then changed a bunch of shit. But either way, Deb packages on Ubuntu. You can still follow along if you built from source, but the path to your setup files will likely be different. You also won't be able to use the sudo apt install ROS something distro something package command used frequently in the beginner level tutorials if you install from source. If you are using Linux or Mac OS but not already familiar with this shell, this tutorial will help, but I'm assuming. I am familiar with the shell. I don't know about y'all, but I'm familiar with the shell. So, first thing we do, we source the setup bash script from our ROS2 installation. So it installs to opt ROS release name by default. We call setup.bash. So that's probably the same thing over here. So in this container, it probably put things in ROS. Yeah, there we go. It put everything in opt ROS Jazzy, and then we would source setup.bash. But it's I'm almost certain that the container here is going to have done this by default. I'm assuming it probably ran this ROS2 entry point shell script. So if you look at that, yep, we can see that, yeah, it's set-e, source opt ROS distro setup exec, whatever you passed it. Okay, cool. So it does source this by default. That's where that came from. And so now we can look at the environment variables just to know. So printenv grep ROS. Oh, that's a lot of stuff. Okay, so specifically ROS version 2, ROS Python version 3, and we should see a ROS distro Jazzy. ROS distro Jazzy. There we go. The ROS domain ID. So ROS automatic discovery range is set to subnet. Okay, so one of the big features of ROS, especially ROS 2, is automatic discovery of services across multiple systems on the same network. So the idea is if you have multiple machines inside of multiple logical computers inside of a robot that are communicating over a network, services can automatically discover each other within the robot without needing a specific master or controller master or whatever machine. Because if any of you have used ROS 1, you would have to run the ROS, I can't remember what it was called, but basically the ROS master daemon, and any machines that would communicate with it, you would need to pass user host name, port number, it's ROS master 11311, right? And then so this domain ID, I believe, lets you define the point of this. I did look at this, but the domain ID is essentially a way that we can define kind of almost like a robot ID. If you have multiple machines that are on the same network that are logically different robots, you would need to set a specific you'd need to choose a domain ID per robot, so that the services on each robot aren't accidentally discovering the services on the other robot. I mean, maybe you would want to do that for some reasons, but just by default, it could easily trip you up if you're not expecting it. So we can set domain ID, although right now, ROS automatic discovery range subnet, which means it'll try to, ROS2 communication is not limited to local hosts. This environment variable allows you to limit the ROS2 discovery range. So it's set to subnet, which means it'll try to discover everything on the local broadcast domain. So if you're, if you're 192.168.0.1, /24 subnet, it would try to find everything on 192.168.0.x, right? But the thing is, we've also put this in a Docker container right now, which means it won't be able to discover anything. But unless we set the how the network can leak out of Docker, we'll need to rerun this with the host mode, or the network mode is a host, or I wonder, IP. Oh, it's not even. Okay, if config. Wow. Okay, they don't even give you those bits. Okay. See what it looks like if we look at my IP config. Yeah. Okay. It did create a virtual Ethernet link. We ping Google. It probably doesn't even have ping. Okay. Yeah. Okay. So we'll have to remember some stuff. But anyway. All right. So now that we have a working installation, we go and look at the Turtle Sim tool. So The next tutorial here is called Using TurtleSim, ROS2, and RQT. Which, maybe this is pronounced RQT, maybe it's pronounced Racket. I don't know. I might call it Racket at some point because it might be funny. But anyway, we'll exit this container. And just as an example of running things with... so this is a... We'll get into this, but I was experimenting with this earlier. But basically... trying to get 3D acceleration inside of a Docker container, but we'll get to that in the future when we need it. But specifically, I was just looking at this network host mode thing here, which should let us. Oh Jesus! So actually, just to start off with this, I'm going to go into my projects folder here, and I'm going to make a ROS2 folder. And what we'll do is we'll make a directory in here and overlay this as like some random directory inside of the container. And this will be where we'll be able to put our workspace. So anything persistent that we want. So I'm going to make here a tutorial folder, or we'll call this tutorials. And then we'll do docker run, docker run OSRF, and we'll remember to put this network host thing in here, which means that this container will run with host networking privileges. So when a service starts in this container, it is using the network device, it is using the external network interface. Or, well, that's not the right way of doing it. So by default, the way that Docker runs things is that it gives each... for every group of containers, you can define them, but for every Docker like network context, it creates virtual Ethernet or virtual network interfaces and assigns an IP address to each of them. Okay, I explained that wrong. Sorry. In Docker, you can define essentially network contexts. Network context you can almost imagine as like virtual networks. So if you're doing Docker Compose, that's your networks entry. And those are essentially the set of services that can see each other to a certain degree. And then for each logical container, each would get a virtual network interface that would then be placed on a bridge that existed as that virtual network context. So essentially, you can kind of think of it as each container gets a port on a virtual switch. The virtual switch is the network context, and the containers cannot see the outside world unless you let them. And for ports to be accessible externally to the machine hosting the containers, part of the Docker runtime, part of the whole Docker startup configuration process is services will say, I want to explicitly expose that I have a service on this specific port. And then the Docker runtime will allocate an external port on the actual like network interface of the machine that's externally visible, and then basically set up port forwarding into this virtual network that it created. That's defaultly what Docker will do. So essentially, containers are completely isolated from the real world unless except for specific definitions of how you let it access. But for things like ROS, where it's trying to do all of the service discovery stuff, that doesn't exactly work very well. It assumes that it has control over the network interfaces. So we have to tell Docker that we don't want this this network virtualization type stuff. So we tell it network mode host, and that's what this will do. We do this, and it doesn't look any different. Well, it actually looks slightly different. See, our host name is now my host name, and not just a random container name. But I guess that either way, that's not that specific part's not important. But I'll pull up another shell here, and this will. Okay, sorry. I need to switch to hyperlink like all of those other cool YouTubers, right? At some point, right? I'm required to, I guess. I don't know. All right, so we're gonna run another. Oh, oops, sorry. So we're going to one last thing I forgot. We're going to set up a container forward, or what the heck are these called? Volume forwarding, right? So we'll add our present working directory, or our present working directory tutorials folder to we'll call it /ROS2 workspace, right? Because that's what everybody calls their ROS2 workspaces, right? Oh, oops. That wasn't the right syntax. Okay. I didn't do this right. Yeah, I didn't do this right. Okay. Oops. Network hosts, present working directory. Now we would do OSRF / ROS Jazzy ROS Jazzy desktop full. All right. And so now we should have a ROS2 workspace folder, which we do. Oops. Or ROS2 workspace, which we do. All right, cool. And we're going to go to projects, tutorial, or projects, ROS2. Oh, tutorial. Oh, it'll automatically create a directory if I didn't have it there. Okay, well, we'll remove, just because we did this wrong, we'll remove that tutorials folder. So again, we'll do docker run network host, tutorial. Now we have another shell. These are two separate instances of a context, by the way. But because we've now got this, we have our environment. We have our Docker shell here. So we'll install turtle sim. So apt install ROS Jazzy turtle sim. Turtle sim's already installed because I did full. Remember, it should install everything. So ROS2 package executables turtle sim, right? Turtle sim. All right, so we have draw square, mimic, turtle teleop key, and turtle sim node. Actually, let me read the background here, right, for y'all, right? Okay, so background. Turtle Sim is a lightweight simulator for learning ROS2. It illustrates what ROS2 does, and at the most basic level to give you an idea of what you will do with a real robot or a robot simulation later on. The ROS2 tool is how the user manages, inspects, and interacts with a ROS system. It supports multiple commands that target different aspects of the system at its operation. One might use it to start a node, set a parameter, listen to a topic, and many more. The ROS2 tool is part of the core ROS2 installation. RQT is a graphical user interface, or GUI, tool for ROS2. Everything done in RQT can be done on the command line, but RQT provides a more user-friendly way to manipulate ROS2 elements. This tutorial touches upon core ROS2 concepts like nodes, topics, and services. All of these concepts will be elaborated on in later tutorials. For now, you will simply set up the tools to get a feel for them, and that's what we're doing, because I have not gone through these in a decade. All right, so in the previous tutorial, configuring the environment, we configured the environment. Now we're in here. As always, start by sourcing your files and install turtle sim, and now ROS2. Oh, this isn't going to work because this is a container with no head. So we'll just see what happens. So turtle sim node, turtle sim node. Okay, couldn't connect to the display because it's a container. So let's actually bring up that horrid mess of crap from this. We'll exit this. So yeah, we're gonna pause the tutorial just for the moment. We're going to futz around with trying to get X support inside of a container, which we can do. So I'm gonna run the first little magic command that you need to know, and that's X host plus, which lets other machines use your other users even use your X session. And because the Docker container is another user. So access control disabled, clients connect from any host, which probably security vulnerability. But anyway, so now we're going to look at our little handy dandy Docker run command that we did. Then we're going to look at this one that I made above. So Docker run it network host device equals dev dri. So we're bridging in our Linux DRM system, which is Direct Rendering Manager, not Digital Rights Management, but our Linux Direct Rendering Infrastructure folder, so we can get our graphics card stuff. We're going to add the video group, because that's the user that all the DRI tools are created under. Volume equals, that's, so temp.x11 Unix /temp.x11 Unix. This will give us our X11 sockets. E display equals display. That'll bring over our X display variable. We're going to ignore the Wayland display for right now. I mean, why not? Why not? We'll bring it over. Wayland display equals Wayland display. Another volume for. That's funny that I spelled out volume all the way up here, but dash v xdg runtime dir / Wayland display to xdg runtime dir / Wayland display, and then now we can do our volume for our WD tutorial, map that to / ROS2 workspace, and then OSRF / ROS Jazzy desktop full. Oh, that didn't work. -- v. Oops, sorry. Put too many dashes on this one because I was removing volume. All right, that came up. So now let's try to run Turtle Sim again here, and see if we actually get a window. I keep wanting to call it Tutorial Sim. Turtle Sim node. We got a Turtle Sim. We're forwarding. What do you call it? We're doing evil things and forwarding our X11 session from our host into our container, which is hilarious. But either way, that's how we do it. We basically to go through here again just to explain. Temp /.x11 Unix is a temporary directory created where X11 will put all of the sockets to communicate with the X server locally. The display variable is tells X11 applications which X server to connect to. Wayland display is effectively the same thing but for Wayland. And then volume xdg runtime dir / Wayland display, you can imagine is the exact same thing as this temp X11 Unix, except there's a separate directory created per user per screen. So we just need to make sure that all of these come over. And then device DRI group add video, that brings in the dev DRI nodes that let you control graphics on Linux. Yeah, so that Danish, that's actually quite correct, or that's a pretty good way of looking at it. Even if we go back to that Docker recommendation thing here, like literally the example is, if you're going to use Docker and ROS, you might as well just put each service, basically each node or service inside of its own container, because why not? Just to reiterate for anybody who might have just joined, the reason that we're using Docker here is that you're perfectly capable of installing ROS on your desktop, but the thing is that ROS is extremely married to Ubuntu. So in a lot more fundamental of a way than most like Linux applications are tied to any given distro. Like there are ROS tools that kind of, they don't necessarily expect to be able to call Ubuntu tools, but there's a lot of stuff that all the documentation will call it, hey, install this Ubuntu package to do this thing. Hey, install this other thing. Even all of the build tools for ROS are only packages, Ubuntu packages. They literally just say, if you want to do it in another distro, have fun. Like, here's the source, we're not supporting it. So in a lot of ways, you're inviting a lot of trouble for yourself. You'll spend just as much time debugging like differences between Ubuntu and whatever distro you're running than you will actually writing your robot code. So if you just don't want to worry about that in the first place, you might as well just use Docker to isolate the fact that you need to run ROS nodes on Ubuntu from whatever Linux you choose to be running on your desktop. And I'm not running Ubuntu, and I'm not going to say what I'm running right now because I don't want to start a distro argument, because that's not what I'm trying to do. But I don't feel strongly one way or the other. I'm just not running it. So we gotta. I'm trying to teach you how to deal with that fact. Also, it's helpful with the robots because one of the big things too about building about using Docker is that Docker has infrastructure to build Docker containers, obviously. Well, or specifically, if you have a Docker build file, you can compile. You can if you define a file on how to compile all of the software that goes into a Docker container, then you can run that tool as whatever target architecture you want. It natively, implicitly supports cross-compilation. So the Raspberry Pi, admittedly the Pi 5B is the fastest Pi yet, as every new Pi is the fastest Pi yet. But the thing is it's like, and while you can reasonably interactively use compiling software on a Pi these days, it's not so bad. But the fact that, okay, my desktop is a 16-core AMD system from 2 years ago, like, it will compile software like that. It'll take it seconds to compile what it'll take the Pi minutes to compile, right? So you can, or maybe even that, maybe even more. I've got 4 times the cores, and they all run like however much faster a Zen 4 core is compared to a Cortex A76. But running it is twice the frequency and a lot more. Either way, it's useful for distribution as well. Distribution and compiling software, because you can compile all of your containers for whatever target architecture on a much faster machine, and then just shuffle it off over to a slower machine to run it. But either way, that out of the way, Turtle Sim is up, and spawning turtle with node name turtle sim, and spawning a turtle at a place. And then this AMD GPU thing is there be dragons by doing this whole thing that I'm doing. Yeah, I think I remember you telling me that one, Danish. Sure, yeah, it's like saying that HTML is XML. Like, that'll help you do a website. I don't know. Either way, so now, just to demonstrate this multi-container thing that we're doing, right? So we're going to do ROS2 run. We're going to use the other container to run. Oh, I didn't run the container yet. Okay, Docker run. Oh, let me copy the run command out of this other terminal here. So over here, all right, we now have another instance. We'll go to our workspace. We don't actually have to go to our workspace yet. I think that's the next tutorial. But anyway, ROS2 run turtle sim, tutorial sim, turtle sim. Turtle sim turtle teleop key. All right, and now we should be able to use stuff to control. Okay, I swear to God, none of the people that write this robotic software has ever played a video game, because all of the commands that I keep seeing in all these keyboard control programs are not only not the same, none of them are ever the same as video games either. It's like, come on, give me WASD, WASDF, right? WASD. Either way, okay, so what does G do? G, B, V, C. Oh, wait. F to cancel, or Q to quit. Nope, that quit, but rotate to absolute orientation. How do I control the turtle? Okay. At this point, you should have a turtle terminal running telop key. You can use these, arrange these windows so that you can see the turtle sim window, but also the turtle running telop. Okay. Okay. Keys to rotate to absolute orientations. Maybe it's trying to directly hook the keyboard input, or do I have to hold the key? No. Well, this is doing something. Well, it's doing a whole lot of nothing. Well, huh. Now we gotta get into debugging. All right, no, okay. Use the arrow keys. Okay, that's definitively not working. So, I wonder how turtle telop key is actually accessing the keyboard. Because it might. Okay, if it's actually okay, here we'll do this. Another disgusting, horrible thing. We're going to do. Right. Dev event or dev input, right? Yeah, all right. So Docker run. So we're going to add the keyboard. We're going to add all of the input devices to our container as well. Group add input. Oh, I didn't like that. Response from Damon, unable to find group input. Oh, well, that's fine. Whatever. Hey, now let's run. Well, right, it's a new container. It's a new container instance. We'll lose our command. Right, these are every time I exit the container and I restart the container. It's like I've started up another OS instance. Okay, that's not working either. Okay, Q to quit. EV test. Okay, apt install EV test. You booger update. Ooh. Alright. Apt install EV test. There we go. Let's use EV test. See if we can read stuff. USB keyboard, right? Input 6. Yeah, my keyboard's working. Okay, it can... I don't know what this turtle sim... Oh, I need to use the arrow key. Nope, arrow keys aren't doing anything. Arrow keys aren't doing anything. Arrow keys aren't doing anything. Alright, well, that's annoying. Maybe it can't talk to the other thing. Okay, what happens if we kill Turtle Sim over here and start tell up? It starts. Okay, we may have the surfaces not discovering each other. That could easily be what it is. So we'll actually run Turtle Sim here again. And then it's telling me to run ROS2 node list. And it doesn't show any nodes. Okay, that's... Okay. So let's set that domain ID. ROS domain ID equals 1. Let's set domain ID. Export ROS domain ID equals 1. Let's see if that helps. Nope, didn't help. All right. So I'm already... I know Danish is laughing that I'm already having trouble because of Docker. Man. I've done this before. Okay. Let's see here. Host network, dev, dr, do all the things. Okay, so... Image, command, services. I mean, you're supposed to just be able to do the thing. Let's see. RM, interactive mode. Well, these are all saying that... Okay, well, actually, we're going to take off that host network thing right now because, at least for now, we only have to worry about working inside of my machine. And, I mean, this is what the other machine is saying. This is what this tutorial is saying to do. So, we'll do that. Yeah... Okay, so we've just gone through and removed the host networking thing from here. We're gonna rerun our ROS2 run turtle sim. No, I don't want AI synopsis. I want copy. There we go. There we go. Turtle sim node. Oh, it's got little thrusters on it. That's cool. I do ROS run telop key over here. Hey, now it's working. Okay, cool. So it was clearly a node discovery issue. I mean, we knew that, but anyway, we knew that, but the question is why? Why was it having troubles? I mean, if it was running on the host, they should have been able to discover each other. Let's pull up. Let's Google that real quick. So let's see, ROS2 Docker host networking, 2 container nodes in 2 containers can't see each other. Network equals host, and they cannot see each other. It's often this is a DDS implementation. Mount, if the containers are running as different user IDs, or if dev shim is not properly shared, shim communication can fail. Shim big shared memory. Okay. IPC equals host as well. Okay, so let's try that, because while running things in containers is definitely a good thing. I mean, using isolated containers is definitely a good thing. I really do want it. If I'm running ROS nodes on the Pi, and I'm trying to use a visualization tool over here, I have to use that host mode networking. Otherwise, the containers on my desktop won't see the containers on the Pi. Forget containers on the Pi. Even if we're not using containers, we're just running ROS2 directly on the Pi, we won't see the nodes and services on the Pi. So, right, so we're going to do network equals host, and then IPC equals host, which is the new thing that it's saying to do from this little help here. Dev Shim is just joined in. Are you running a graphical app from Docker? Yes, I am. So we did that by doing this huge command line add here, where we're like add device equals dev DRI group add video, and then that adds the directory where the GPU graphics card control nodes are in Linux. The DRI stands for direct rendering infrastructure. So yeah, we basically tell Docker to import those device nodes for the video card. And then we add my WAN with it's working. Oh, so you missed the whole thing. Fantastic. Okay, Danish. But anyway, yeah. Then we have adding a volume for temp/.x11 Unix, and then xdg runtime dir/Wayland display, mapping that stuff into the container, and then also running this little command called xhost plus. Never thought this possible. Sounds like an X11 thing. Well, actually, you can do it on both X11 and Wayland, because we're not actually X forwarding. What we're doing is we're actually adding all of the device nodes, and we're bringing in the Unix sockets that let you communicate with the host's X server. We're forwarding those into the container. So the containers will even have 3D acceleration, which you wouldn't get with X forwarding. The reason that we want to do this is obviously ROS has a lot of graphical tools, specifically RViz uses OpenGL, but so they're just only called xhost. If we run all that, we can run stuff in here. And just to prove that, if we do apt update and apt install glmark, I'll show you that we can definitely run OpenGL from a container. So you can see we're as soon as it installs. See, we are in a container, and because this is Ubuntu, and I'm not running Ubuntu, but I can run glmark, and there's 3D from a container. Okay. So, and it's, yeah, and, okay. Anyway, so, where am I going with this? Right, okay, so we've done this network host, IPC equals host. This IPC equals host should bring over the dev shm directory, which is where, at least with Ubuntu, where it mounts, where it puts shared memory objects. And one of the big things about ROS2 is that they rather than everything being network over a network by default, it's they supported shared memory pipes and Unix sockets and things. Just it's for more efficient to be more efficient because that was always one of the big complaints about ROS1 was that everything had to be moved over a network, even if it was like local to local and you weren't trying to talk to machines that machines outside of your current like machine, or even if you only had one machine in the robot, even though you had multiple nodes, they always had to use a network to communicate with each other. Now those packets wouldn't leave the robot, but like you'd add the inefficiency of like, okay, I'm talking a TCP to another process on the same machine. Why am I doing that? So anyway, lots of uses of shared memory and other types of inter-process communication on ROS on ROS2 over ROS1. Okay, so just to double check, Docker run and actually, okay, let me exit that again. Docker ps. Oh, good lord. Okay, so I forgot to put the --rm thing in Docker, so every time I run Docker, it's going to, oh dear. Docker ps-a. How do I use awk? Is it print 1? No. Oh well, I can't remember. It is not important. I gotta go and figure out how to remove all of these container IDs. Okay. Docker remove all containers? No. Exited containers. Oh, here we go. Docker container prune. Oh, that might take a bit. Yeah, you know, honestly, one of the things I use awk for, the only thing I really use awk for is to print out columns of text. Like, if you've got one of these where, okay, here's, you know, the first block is something, the second block is another thing, and, you know, it at least it's unified in that way. Like, I use awk to be like, print the first column, you know, or take, oh, that's taking a bit. I hope I didn't just screw myself up. Okay, I'm gonna turn on the lights, starting to get dark in here. Alright, there we go. So, that's taking a scarily long time. I'm gonna stop that. Oh dear. I've really done it now! Okay. Okay. Here. Okay, we'll just deal. We'll just deal with it for now. Okay. Just to figure out that awk thing, just to try, awk print first column. Just to be fun. Awk print. What? I almost had it. It was lower. Was it lower? What did I do wrong? Pipe awk print. Oh, I was supposed to put the whole thing in those the bracket, the curly braces. There we go. Print column 1. Yeah. But anyway, Docker. Right, run network host. We're gonna put the --rm in here too. All right, so we got our thing there. We got our thing there. The ordering doesn't matter. I'm just have OCD. Okay, so we'll go back to our tutorial. Turtle sim. We'll run turtle sim from in here. Oh, that's the controller. Tell op key, but we don't want to do that before. Sorry, we want to spawn the turtle first. Start turtle sim node. All right, we got our little turtley boy here. We've got our teleop key here. Or actually, before we do that, ROS2 node list. We see the turtle sim node. Okay, cool. Okay, cool. So we're now running host networking mode. We needed that IPC thing. Okay, cool. So that's all we needed. So now we've got the big, long, horrible Docker Docker invocation here. You know, this is fun enough. I'm just gonna post it in comments. Oh, It's too long to post it. Okay, thanks, Google. Okay. Well, have fun typing that. Okay, so we're gonna bring up another terminal and load up another Docker instance here, and then so if we do ROS2 node list, we can see that we have the teleop turtle node. We can see that we have the turtle sim node. If we do ROS2 topic list, we see that we have parameter events, whatever that is, ROS out, turtle1 command velocity, turtle1 color sensor. I don't know what that does. Turtle1 pose. Maybe color sensor returns the color under the turtle. I don't know. And then we've got ROS2 service list. Oh, wow, okay. Teleop turtle describe parameters, get parameter type. So our services that are available. And then ROS2 action list. Turtle1 rotate absolute. Okay. Okay. So you will learn about these concepts in the coming tutorials. Since the goal of this tutorial is only to get a general overview of TurtleSim, you will call RQT to call some of the TurtleSim services and interact with TurtleSim node. Okay, so we could install RQT, but we used the Jazzy Desktop full instance, or container, so it should automatically be installed. So maybe we can run RQT. We can. Okay. So yeah, more GUI stuff from Docker. All right. So it may take some time for RQT to locate all the plug. Okay, sorry. When running RQT for the first time, the window will be blank. No worries. Just select plugins, services, service caller from the menu bar at the top. Then we get stuff. It may take some time to locate all the plugins. Well, it didn't. If you click plugins but you don't see services or any other options, you should close RQT and enter force discover. But it worked, so we don't have to worry about that. All right, so clear topic. Okay, so service. I don't see a clear service, but oh, there we go. We refreshed. Now we can see all of the stuff. Teleop turtle kill clear reset. Okay, sweet. Try use the refresh. Oh, use the refresh button to the left of the service dropdown to ensure all the services of your TurtleSim node are available. Click on the service dropdown list to see TurtleSim's services and select the spawn service. That better create a new turtle. Is the turtle named Sheldon? Sheldon. Yeah. Well, we can call him Sheldon. Well, when we create a turtle, we'll call him Sheldon. How about that? So now enter some valid coordinates to spawn the new turtle, like give the turtle a unique name like Turtle2. No, we're calling him Sheldon, as you said. We'll use lowercase, though. Sheldon. We'll spawn him at 1. 1. And theta is 0, so rotation of 0. And then what if we call that service? We have a turtle! Spawning turtle Sheldon at 110. Okay. Error, a turtle, and if we try calling it again, turtle named Sheldon already exists. Okay. To spawn Turtle2, you then need to call the service by clicking the call button, which we did. If the service call was successful, you should see a new turtle, again with a random design. Spawn at the coordinates you input for X and Y. If you refresh the service list, we should see there are now services related to Turtle2, or in our case, Sheldon. Okay. In addition to Turtle1, let's give Turtle1 a unique pen using the set pen service. So Sheldon set pen. And so we're going to give him a... Well, it's using red, so we're going to give him green, because we got to do something different than the tutorial, right? To prove that we're actually reading it. And then the width will increase to... Well, it says 5, so we'll do 5. RG&B, width sets the thickness of the line. To have Turtle1 draw with a distinct... Oh, this is the well... Okay, so this was setting the pen for Turtle1, but we're setting Sheldon's pen to blue. So we'll call that. Response. Okay, now let's set Turtle1's pen color to... We'll give it a red pen. We'll just copy that. Fine. Now we'll give it teal. 255, 255. No, teal would be blue-green, right? And then width of 5. And, okay. Set pen. Okay. If you return to the terminal where teleop key is running and press the arrows, Turtle 1's pen has changed. Yes, it has in fact changed. It is now teal. Cool. And then you've probably noticed that there's no way to move Turtle 2 because there's no teleop node for Turtle 2 remapping. You need a second teleop node in order to control Turtle 2. However, if you try to run the same command as before, you will notice that this one also controls Turtle 1. The way to change its behavior is by remapping the command velocity topic. In a new terminal, source ROS2 and run, so let's give ourselves another container. Run. And in our new terminal, we'll run ROS2 run turtle sim turtle teleop key ROS args remap turtle 1 slash command velocity colon equals Sheldon command velocity. So this should move Sheldon. It moves Sheldon. Okay. Now we can control the other turtle. We control that turtle with that window. We can then control the original turtle with this window. Alright. Cool. Turtle. Okay. So now you can move Turtle 2 when this terminal is active, Terminal 1 when the other terminal is active, and now we can close Turtle Sim. And we do that by closing the terminal and hitting Q in these other terminals. And we'll close Racket or RQT as well. All right. Sweet. Next steps, now that you have Turtle Sim and RQT up and running and an idea of how they work, let's dive into the first ROS2 concept with the next tutorial, Understanding Nodes. All right. So, that works for me. All right, so we're at 7:05. That's fine. Over the next two tutorials, you will learn a series of core ROS2 concepts that make up what is referred to as the ROS2 graph. The ROS graph is a network of ROS2 elements that process data together at the same time. It encompasses all executables and the connections between them if you were to map them all out and visualize them. Nodes in ROS2. Each node in ROS should be responsible for a singular modular purpose, e.g. controlling the wheel motors or publishing the sensor data from a laser rangefinder. Each node can send and receive data from other nodes via topics, services, actions, or parameters. A full robotic system is comprised of many nodes working in concert. In ROS2, a single executable, which is a C++ program, Python program, or something else, can contain one or more nodes. So a single executable can contain one or more nodes. Okay. The previous tutorial shows you how to install the Turtle Sim, blah, blah, blah. Okay, don't forget to source ROS2 in every new terminal. The command ROS2 run launches an executable from a package. So we'll rerun our ROS run Turtle Sim node, right? Because that's what we did before. We'll have Turtle Sim again. And then in the Turtle Sim window will open, as you saw in the previous tutorial. Here the package name is Turtle Sim and the executable name is Turtle Sim node. However, we don't know the node name. You can find the node names by using ROS2 node list. So we'll do ROS2 node list. Turtle Sim. Okay. We'll show you the names of all the running nodes. It's especially useful if you want to interact with a node or when you have a system running many nodes and need to keep track of them. Open a new terminal while Turtle Sim is still run ROS2 node list, which I just did. Open another window. Well, we already brand teleop key, so I won't make everybody look at that again. We're referring to the turtle. Remapping allows you to reassign default node properties like node names, topic names, service names, etc. to custom values. In the last tutorial, you used remapping on turtle teleop key to change the command velocity, topic, and target Turtle 2. Now, let's reassign the name of our Turtle Sim node in a new terminal. Okay, so in a new terminal, we'll do what we did with RQT. This is going to open up a new turtle sim instance, I bet. So we'll do it from here. So ROS2 run turtle sim node ROS args remap node equals my turtle, or yeah, fine, my turtle. And we have a new turtle sim instance. Okay. And if we were to look at the node list again, we should see 2 turtle sims, which we do. My turtle and turtle sim. Alright. So then we can look at node info. Now that you know the names of your nodes, you can access more information about them with ROS2 node info. Node name. So we'll do turtle sim. Okay, no, it tells me to use my turtle. My turtle. Okay, my turtle. It subscribes to parameter events, which is RCL interfaces, messages parameter event, subscribes to turtle1 command velocity, which is a geometry message twist. Interesting. Publishes log messages and publishes the output of a color sensor and its current pose. And then service servers. I mean, services. Servers, services. Okay. And we got turtle1 teleport and action servers rotate absolute. That's probably what those keyboard commands would do. Okay. ROS2 node info returns a list of subscribers, publishers, services, and actions, the ROS2 graph connections that interact with the node. Now try running the same command on the teleop turtle node, and it should be kind of the same thing, right? Teleop turtle. Wait, what? What? Oh, I didn't try. Did it tell me to restart the keyboard? Okay, well, okay, it assumed it still had the keyboard running in the background, so. Enable. Fine. Fine, ROS2 run. Turtle sim. Turtle teleop keyboard, right? No, that wasn't it. Teleop key. Right. Then we can look at teleop turtle, which subscribes to parameter events, publishes turtle1 command velocity, which is a twist. So this publishes command velocity, and this subscribes to command velocity, and that's how the data gets from this node to the other node. Action clients rotate absolute. So action. Oh, and it can. So it's a client. So an action server is a node telling another node to do something. So this serves rotate absolute, and this subscribes, and this is a client to the rotate absolute action. Okay. All right, and now that you understand nodes, let's move on to the topics tutorial. Next. Okay. Yeah. Okay, use RQT graph and command line tools to introspect ROS2 topics. So, a node may publish data to any number of nodes and topics. A node may publish data to any number of topics and simultaneously have subscriptions to any number of topics. It doesn't have to be one-to-one. Multiple people can connect to, multiple subscribers can connect to a publisher, etc. And this is called a pub sub model, also known as data distribution system, as a number of things to call it. Anyway, topics are one of the main ways in which data is moved between nodes and therefore different parts of the system. The previous tutorial provides some useful background information on nodes and is built upon here. As always, don't forget to source ROS2. Okay. So we're gonna keep our turtle sims that we had open previously still open because this tutorial reuses them again. And okay, so we've got a teleop key to move. Oh, look at that. They both listen to the same inputs though. Interesting. Even though there's two node names. Okay, well, interesting. Well, we'll kill the remapped one, right? Okay. So, we have a teleop key. It does a thing. Right, because the turtles are named the same thing in each of them, right? Okay, okay. I just want to play with this. Okay, so we've remapped this to my turtle, right? So, but now teleop keyboard is going to control both of these, even though they're different spots, right? So if we were to... Let's reload RQT from before, right? Okay. So, plugins, services, service caller. We'll refresh. What if we kill... we kill Turtle 1. Ah! No! Shit. Okay, can we restrict kill to only a specific Turtle Sim instance? I don't know. Anyway, okay, fine. We got to respawn a turtle. Come on. All right, so we'll spawn. We'll just reboot the stack here. Okay, kill Turtle Sims. Open Turtle Sim. I want the turtle with little rocket boosters on it. So let's keep rerunning this until we get turtles with rocket boosters. Oh, it's like a... What is that? It's like a spiky turtle. There we go. Rocket booster turtle. Okay. Kill... we still got teleop keyboard running too. Okay. So. Now we're going to do ROS2 run RQT graph. RQT graph. Okay. And you can open RQT. Oh, so it's a visual tool for displaying the data graphs inside ROS. That's cool. So you can see how all the connections work. And what happens if we spin up another instance of Turtle Sim again? And then refresh this. Look at that. Okay, so teleop turtle, which is our keyboard thing that we spawned, publishes to both turtles. That's cool. Or it's cool that we can see that via a visual tool anyway. Okay. So let's kill that and let's see what this has us do. So you should see the above nodes and topic as well as the two actions around the periphery of the graph. Let's ignore those. If you hover your mouse over the topic in the center, well, oh, there we go. We shifted this to nodes topics active. You can also open RQT graph by opening RQT and selecting plugins introspection node graph. Okay. You should see the above node periphery of the graph. It didn't tell me to select nodes topic active. I just went to what it was showing in the picture. But okay. So if I make this wider, does it change or group 0? Oh, there we go. Okay. So if I set all of these to what it looks like in the picture over here, then we get the same picture, right? Okay. So if you'll see the color highlighting in the center. The total is publishing data, the keystrokes. Command velocity topic in the node is subscribed to that topic to receive the data. The highlighting feature of RQT is very helpful when examining more complex systems with many nodes and topics connected in many different ways. RQT graph is a graphical introspection tool. We'll now look at some command line tools for inspecting topics. And let me go grab the battery because I hear the battery charger beeping. All right, I'll be right back. Then I'll answer your question when you're back. Oh no, I have awoken the kitties. Hi, babies. Alright. Grabbing the robot. Alright, turning the webcam back on. Okay, there we go. The kittens have awoken. Oh no. They're terribly cute, but they're also... What am I doing? Right. Okay, strapping the... We're just putting the battery back in the robot. Alrighty. Got that in. Battery cable. Plug. I could have designed this a little better, but anyway. Hey. The battery is installed. Sweet. Now let's plug in the silly question. So you will be programming each turtle to simulate it. Okay, now we are realistic. I mean, if you're using Turtle Sim, yes, but what we're doing here is we're just I have not used ROS on a real robot in a very long time, and I mean I've never used ROS2 like at all. Like the last thing I worked on was God, what was it called? It was called PR2 Lite. 2 Lite. What was it? PR Lite, not PR Lite. Hold on, read the latest update. Okay, yeah, here we go. Yeah, 2014, right? This is the last update. So we built, my friends and I here built, we were trying to essentially make a cheap version of Willow Garage's PR2 robot, which was PR2 was a big $400,000 robot, you know, very expensive that no hobbyist could ever possibly hope to even think of getting. So we built this thing, which cost like $3,000, not $400,000, and it could run a lot of the same software as. Oh yeah, we did take this to Robo Games. Oh, this was just after I finished high school, but either way, yeah, we were building this. This is the last time so yeah, 2014 was the last time I really did anything with ROS, and that was ROS 1. So we're doing ROS 2 now, and they changed so many things with ROS 2. So we're basically just going through the tutorials, is all we're doing from the beginning. So yeah, if you wanted to write little programs to control the turtles, like you could do that. It's a basic simulation environment. But realistically, we're just using the Turtle Sim. We're just going through the tutorials, and the tutorials use Turtle Sim because we want to get to programming this thing, but I'm just trying to go through here so that we can be familiar with all the ROS2 terminology and things, so that when some tutorial on some package we inevitably end up using says do this, I'm not entirely lost. So just rolling through these tutorials as quick as we can, just to kind of learn some things about what's going on. And let me grab my pliers real quick so that I can install the SD card into this robot. Okay. Pliers. The only reason we need to use pliers is because I decided to go and put the way to access the SD card in a really hard to reach place. So it's in the back of the Pi here, so let's get get this in here. Get in there. Hold on. Okay, hold on. No. Shoot. All right, let me at least turn the camera back on. Okay, we're trying to wiggle a micro SD card into a slot in here. Oops, dropped it. Okie dokie doke. Here. Okay. Come on. Come on. Get in there. Oh, almost. Maybe I can wiggle my finger in here and get it in. Get the stupid SD card. Hey, there we go. Got it. Okay, perfect. I got the SD card in the Pi. I'm gonna plug the Pi's power cable back in. And then, all right, that's that. Our battery is plugged in. Should be able to turn on the robot. And the lighter starts to spin up. But, okay, so we're mainly in here, or we're mainly looking at just, what do you call it? We set up our Pi to use the hostname Stinger, so eventually we're going to try to, whenever it figures itself out, we're going to do ping stinger.local. Local. And it'll probably take it a couple of minutes to do its first boot, so we'll just leave that there for, let me close that terminal so it's not floating around here. But, okay, anyway, continuing, we've got ROS2 topic list. Okay, where's a terminal that is not busy? Here we go. ROS2 topic list. Okay, so we got our command velocity color sensor pose. Okay, list-t, but this time with the topic type appended in brackets, so it gives you the types. These attributes, particularly the type, are how nodes know they're talking about the same information as it moves over to the topic, so it's just name type transfer. Okay. And these attributes, okay, if you're wondering where these topics are in the RQT graph, look at the boxes under, uncheck the boxes under hide. What? Under hide. Oh, uncheck the boxes under hide. Okay. Hide all of this stuff. Okay, cool. We see all of these things going to ROS out as our parameters, or our logging server. Okay. Perfect. Then we can echo the data being published on a topic. Okay. So if we re-hide all of this stuff, then we do ROS2 topic echo turtle1 command velocity. Do ROS2 topic echo turtle1 command velocity. And then if we type things into that keyboard again, the keyboard control, then we should see data coming out, right? Hey, we do. Okay. So we can now see all of the control outputs coming from the keyboard by echoing that topic. Well, we never actually tried to do the absolute orientation. G, B, V. Oh, that's cool. Okay, cool. So that's what that does. We see all that stuff coming out. Now return our RQT graph and uncheck the debug box. And ROS2 CLI daemon is a node created by the echo command we just ran. The number might be different. You can see that the publisher is publishing data with the command velocity topic, and 2 subscribers are subscribed to it. Well, tell up turtle command velocity. Wait. ROS out. Unreachable transform params. Okay. Tell op turtle goes to the anyway. ROS2 topic info. Gives us tells us one publisher, one subscriber. So if we were to do that echo thing and then go to a free or terminal that wasn't doing something, they're all doing something. So we need another ROS terminal or Docker container. We'll do ROS2 topic info turtle 1/command velocity. There's 2 subscribers now because we have that echo topic, that echo command listening. All right. ROS2 interface show. Nodes send data over topics using messages. Publishers and subscribers must send and receive the same type of message to communicate. The topics we saw earlier after running ROS2 topic list-t tells us what type is used. So recall that command velocity had the type geometry messages message twist. This means that the package geometry messages, there's a message called twist. Now we can run ROS2 interface show geometry messages message twist. This expresses velocity in free space broken into its linear and angular parts. Linear velocity xyz, angular velocity xyz. Okay. This tells you that the turtle sim node is expecting a message with 2 vectors, linear and angular, of 3 elements each. If you recall the data we saw tell op turtle, passing turtle sim to do, it's the same structure. Now that you have the message structure, you can publish data directly to a topic from the command line. Okay. So ROS2 topic pub topic name message type args. So we can do pub turtle 1 command velocity geometry twist linear. This is JSON, seriously. X 2.0, Y 0.0, Z 0.0, angular 0, Y 0.0, Z. Let me do for Z 1.8. 1.8. It did a thing. Alright. Oh, it's publishing it continuously. Okay, interesting. If we're to publish an empty message. Default is equivalent to doing 0. You can trigger autocomplete. Oh, can it really do autocomplete? Ooh. Twist. Stream working on it, be in a Discord. I mean, that's what I'm doing right now. I need to learn. I need to go through all the tutorials. Let me point a camera at myself and have other people go through the tutorials with me as well. Yeah. Let's see. How do I... Unbearably boring stuff. I mean... I feel like... What is the... Honestly, there have been many times where I've gotten up and just walked away from something, like, because I got bored. But realistically, getting through the parts of projects that are boring is... I think the best way is to just... You know that... Eventually you'll figure out which ones are standing between you and what you need to do. Like, sit down and, like, just make a time. Like, you're like, okay, my project that I want to do is, you know, currently blocked because there's this thing that I don't want to do, but I have to do it before I can actually get to the fun part. Like, I sketch it into your calendar. Like, you know, just, you know, figure out a time that you're going to do it, and then, like... You know that it's going to suck, and you know, maybe give yourself an hour before or an hour after as well, like, you know, kind of like wind up, wind down. But I find it's a lot easier when you decide on a time that you're going to do it. Like, you're making time to do the not fun part. The time is explicitly scheduled for the not fun part. And that seems to work a lot better for me. And as Danish says, honestly, hopping on a Discord call with a friend, and while you're working on it, or even if you're not really talking in the call, like if you're joining a group call or something, group chat or something, just listening to people talking in the background. So it's more like sitting in a coffee shop working on something than it is, sitting alone in your house doing something. Let's see here. Autocomplete with a tab key. Well, that didn't work, but that's probably just because of the Docker container. Okay, well, let's see if the Raspberry Pi came up. So we should be able to ping this stinger.local, which we can. Cool. Stinger.local. So if we do this term equals x term 256 color, because Ubuntu doesn't understand my terminal that I'm using. SSH stinger.local. Yes, we'll add it to the list of known hosts. There we go. We have our Raspberry Pi, our Pi 5 running Ubuntu 2404. This is an 8 gig. I put an 8 gig Pi in here. Okay. Where did I put my 4 gig Pi? Oh. Did the 4 gig Pi I bought actually have 8 gig? That would be so cool. No, it doesn't. No, it didn't. Never mind. This is the Pi that I took out of the thing that Danish gave me. So never mind. This is supposed to be the 8 gig Pi, not the 4 gig Pi. Okay. All right. I thought I was saving the 8 gig Pi for my other robot project, but whatever. I can easily swap them. Anyway, all right, so we got Stinger, and so now we'll go back, installing ROS2. It's fine. ROS2 Jazzy. We'll install the Ubuntu binary installation. We didn't do this before because we didn't need to. So locale is c.utf8 by default already, which is what we need. Actually, no, it's not. We want... make sure you have a locale which supports UTF-8. Well, let's see. I mean, realistically, I want... And I'm in the US, so English US would be the best for me, but... Yeah, okay, fine. Sudo apt update and sudo apt install locales. And then... Enable required repositories. All right, no services are running, and then we're just gonna do that. Copy. Oh, now, all right, sorry. Copy. Calgen TF8. Do this one. And then verify settings. Perfect. English US. Okay. We got to do install the Ubuntu. I did it again. It's Control-Shift-C in the terminal to copy. It's do that in the browser. It opens up the debugging window. And add apt repository universe. And then we got to install some other stuff. Add universe. So, oh, why? Oops, I'm doing this from source. No, we want binary. Ubuntu deb packages. Well, we needed to do that anyway. Wait, deb packages. We need to do that. getting the apt source stuff. Okay. Now we do... Oh, I really, really hate install helpers that are like, here, let's just curl this script into bash. But we're going to do it anyway. Okay. Okay, copy that one, paste that. Install the sources repos for... Actually, this didn't curl. Okay, fine. This didn't curl the thing. All right, apt source. We're going to do update and install ROS developer tools. Another thing that we're going to do, or well, actually, we'll get to... Oh, that's the big one. Okay. That's doing it. Another thing we're going to look up specifically for Ubuntu is a friend of mine. No, that's not it. Hold on. MW34 Ubuntu PPA. Nope, I got the user wrong. Ubuntu PPA Marco Sonic. I'm trying to find a specific ppa.launchpad.net. I think, was it, no, all right, hold on. Okay, hold on, this is wrong. I know, where, okay, sorry. I'm looking for a PPA, which is a personal package archive from a friend of mine. Oh, Marco46. Okay, there we go, fine. Okay. Overview. So, a friend of mine, he has packaged all of the Raspberry Pi, or essentially all of the all of the Raspberry Pi specific packages that are shipped in Raspberry Pi OS for controlling things like the camera. He's packaged so that you can install them on Ubuntu. Noble series. Looking for Marco's PPA. No. Marco Sonic. He's got view package recipes. All right, maybe it was MW46? No, hold on. Let me pull up the... Okay, hold on. Let me check. He posted it in our mailing list on the Homebrew Robotics Club. Hold on. Okay, drinks after the show. Where? Hold on. Okay, Marco. Marco Sonic plus Raspberry. Wait, how did I not find? Okay, either way, that was a long way around. But yes, when Raspberry Pi is done, and where did the Raspberry Pi window go? Hold on. Oh, there it is. Okay, so we're going to add Marco's Ubuntu PPA because we can get all of the camera. We can get libcamera, PiCamera, all of the special Raspberry Pi camera packages that aren't distributed in Ubuntu by default that you need to be able to use the camera on this chip. So we'll do that. 63 packages can be upgraded. Sudo apt upgrade. update, upgrade. All right, it's going to take a little bit to do the update here. It's only coming down at not super fast anyway, but it's coming down nonetheless. Okay, so while that's running, we'll go back to our ROS tutorials here. So all the options can be auto-completed. Okay, I don't really care. As mentioned, the auto-completed stuff we can publish. Twist using that. I mean, the JSON thing looks a lot more straightforward. Turtle and any common linear real bots, which is meant to emulate, requires steady stream of commands to operate continuously. So to get the turtle moving and to keep it moving, use the following dictionary string. Yes, that's what we did. At times you want to publish data to your topic only once rather than continuously. To publish it once, we can use the -once option. So let's bring up our turtle sim again. Our publishy command thing that we did before. We could do pub once. What is the W2? Is that wait for 2 matching subscriptions? This is needed because we have both turtle sim and the topic echo. Oh, cool. There we go. Waiting for 2 matching subscriptions. Publisher beginning loop. Publishing stuff. Cool. All right, and you'll see your turtle move. You can look at the RQT graph. We'll refresh that. You will see the ROS stuff. Command velocity is read by ROS2 CLI, ROS out, parameter events. Cool. Actually, you know what we're gonna do just to test that we're finally okay. Hold on. ROS2 topic find clean up. Okay, well we'll do a little bit more than just this, but okay. So we can do ROS2 topic echo turtle1 pose. Go turtle1 pose, and that should show us. Yes, the position that the turtle is in. There's our teleop keyboard. So if we move the turtle, we can now see that our pose is updating in that one terminal window. Okay, cool. Let's minimize that. Okay, cool. And the publishing message with timestamp, post stamped, topic hertz. That'll just show us the rate at which the thing is published. Interesting. All right. Recall that you set the rate of turtle1 command velocity to publish a steady 1 hertz using pub rate 1. If you run the above command, you'll see it reflecting that rate. So if we do that, 1. Oh, I did that wrong. Oh, it's rate, right? Nice. Okay. Topic bandwidth, and we can measure how much data is being used by that topic. Basically nothing. Okay. And topic find. But I also want to do, since we're doing echo, what is the color sensor? Oh, okay. Okay, so that's... Maybe it's what the robot is currently driving over. Yeah, so, well, that's blue. Huh. Well, yeah, more purplish blue. Okay. And yeah, it like updates if we have it where it kind of stuck on something. Interesting. Okay. Okay. At this point, a lot of nodes running. Don't forget to stop them. Okay. So Oh, and then we can also look up by type. So ROS topic find geometry messages message twist. That'll show us what topics use that type. Okay. So understanding services. Okay. So... Let's see what else is here. Alright, it's almost 8. Okie doke. So we'll close that. We'll close Turtle Sim. Oh, oops. I went back. Okay. I ought to try to close all this stuff. There we go. That's all. Oh, and the Pi is done updating stuff. So let's go back to the Pi. And we'll do sudo apt install. We need libcamera. Libcamera dev. Pi camera 2. RPI cam apps. We're going to do Halo all. I mean, that'll do everything that we need. Wait, what? Lib camera. Why not? Why can't it find lib camera? Lib camera. Oh. Lib camera dev. Pi camera 2. Oh. It's Python 3 Pi camera 2, isn't it? Python 3 Pi camera 2, isn't it? Okay. Yep, there it is. Alright. Pulling even more stuff. Do. Okay, well, anywho, that will install, and then we were going to need to do the big one, which will be ROS2 Jazzy Desktop Full. So that finishes installing stuff. So let's go back to our ROS tutorial. Maybe we'll just quickly read through some of this stuff. Background services are another method of communication for nodes in ROS2. Services are based on a call and response model versus the publisher-subscriber model of topics. While we allowed, updates. Services only provide data when they're specifically called. Prerequisite. Concepts, nodes, and topics. Still need a turtle sim. We're going to have us run turtle sim again. We can see services. Look at a turtle sim's clear service in a new terminal. Kill, empty spawn. Clear. See all the types of services. Set pen, teleport. Standard services serve. Empty. ROS2 service call. Alright, service echo. Service flow style, add 2 ints. Okay. Like a topic, one way communication, next pro. Okay, so basically it's a call and response thing. You define a type that define a call type and a return type. You call something with parameters and it'll send a response type to you back. And then there's some helper, some command line tools to let you see like request sent, response request sent, request received, response sent, response received. Okay. Just gonna trying to save people from too many boring bits here. Learn how to. Oh, and our pie's done. So we should. So let me do something real quick. Vim boot config or boot firmware config.txt. Okay, camera auto detect. Oh, camera auto detect is already turned on. So we should in the in dmessage we should see the camera. Okay, cool. Yeah, sudo dmessage grep imx. We do see the imx 708, which is a PyCam 3 camera module show up. And then I think the one I want to do still is a sudo apt install halo all. Because I think that'll install... Oh god, a gigabyte? Okay, that's fine. I think that will install all the DKMS modules and stuff like that too. This is for the AI hat, which we don't have installed, but I mean, might as well install the tools for it. This is pulling in a lot of graphical stuff that I'm not intending to run on here. Oh yeah, it will pull in Halo DKMS. Okay, cool. That's fine. Perfect. Subtract that for now. Okay. Actions. Or no, parameters, sorry. Actually, let's do this one because I've never used the parameter system before. So run our turtle sim. Oh, that one's got a cool little hat. Alright. So we got ROS2 parameter list. Again. Okay, so that'll give us background blue, background green, background R, holonomic, whatever that means. Quality of service overrides. Okay. You see node namespaces telop turtle, turtle sim, followed by each node's parameters. Each node has a use sim time. It's not unique to turtle sim. Based on the names, it looks like turtle sim's parameters define the background color of the turtle sim window. So if we were to say use ROS2 param get turtle sim, background G shows integer value of 86. You can also set the parameter. So ROS2 param set turtle sim background R to 150. And the color changed. Look at that. Set parameter successful. Now it's purple. We can ROS2 param dump turtle sim. So these are just constants, I guess. Okay. We can have it go to YAML if we want. I mean, it formats as YAML. That's fine. Param load. We can load from a parameter file. That's cool. Load parameter file on node startup. Okay, so let's save this to ROS2 workspace / turtle sim .yaml. Okay, and we mounted this volume in all of the containers. So if we were to say run this again, it'll be blue again. But if we do this ROS_args params file turtle sim or ROS2 workspace turtle sim, it should be purple? No? Oh, do I have to restart the container to see the fact that there's now files in there? Really? Oh. Okay. Answer is no. Did I mess this up? Did I not make... Oh, they're read-only by default, right? No. What? Okay. Tutorial, maybe I have to say read write. Okay. Well, gotta restart turtle sim here. Control C. I'm gonna say... we're going to copy that command that changed the background. No, I did that again. Okay. Okay. Now it's purple. Okay, and then we can do that. ROS2 param dump. ROS2. Oh, turtle sim showed up here. What? Okay. I see what I did wrong. Okay, all of these have been started with present working directory / tutorial. I really hope. How many tutorial directories have I created now? Oh dear, oh dear. Okay. Okay, well, that's fine. We had things mounted as different directories. That's brilliant. So, ROS2 run turtle sim node. All right, and then we did it that way. Then we could do ROS args, params file, ROS2 workspace / turtle sim. And it's purple by default instead of blue by default, because we're loading the parameters file. Perfect. Okay, so that's how that works. Okay, summary. Cool. Okay, so it's just kind of constants, right? Next. Understanding actions. Let's go back to our Raspberry Pi real quick, just so we can finally start the ROS installation. So we're going to copy that, paste this in here. We're going to use full, so it brings in everything. It's going to install 3 gigabytes of stuff. Okay, that'll probably take a while. So actions are one of the communication types in ROS2 and are intended for long-running tasks. They consist of 3 parts: a goal, a feedback, and a result. So it's basically, you tell it what you want it to do, and it sends you intermediate state, and then it eventually sends you the end, I guess, right? No. I think. Goal, feedback, and a result. Actions are built on topics and services. Their functionality is similar to services, except actions can be canceled. They also provide steady feedback, as opposed to services which return a single response. Actions use a client-server model, similar to the publisher-subscriber model, as described in Topics tutorial. An action client node sends a goal to an action server node that acknowledges the goal and returns a stream of feedback and eventually a result. But how do you actually get the result? Because it's clearly you have to query for the result. But anyway, this tutorial builds off of concepts like these are. I think these are new for ROS2. Okay, so we've been using Turtle Sim and telop keyboard. Right? Is that still running on anything? No. Okay. We'll restart teleop turtle. We'll restart teleop keyboard to run turtle sim teleop key. Oh. Ah, what broke? What a spell wrong. Turtle sim. Oh, it's turtle teleop key. Oops. Okay, cool. Alright. So notice that the letters B, C. Okay. So B, C, B. All those use arrow keys to rotate to absolute orientations. Ah, rotation goal received before previous goal finished, aborting previous goal. Oh, okay. So it's an action. It's used actions to define all those little commands of rotation. Oh, and the keys chosen make a box on the keyboard. Interesting. That's what I was trying to make, a box around the F key on the QWERTY keyboard. Okay. Each key's position around F corresponds to the orientation of turtle sim. For example, E will rotate the turtle's orientation to the upper left corner. Corner, pay attention to the terminal where turtle sim is running. Each time you press it, you are sending a goal to an action server that's part of the turtle sim node. The goal is to rotate the turtle to face a particular direction. So, like, action would be move to location, and you'll get the positions as it's moving somewhere. Okay. Between the D key, G key, boarding, ROS2 node info, action servers. Okay, fine. ROS2, action list, then type. Turtle sim, action, rotate absolute. ROS2, action type. Turtle sim, action, rotate absolute. That didn't work. Action type, turtle. Absolute. It tells me, okay. I want information about that action type, though, right? Action info. Action client server. That's what I was trying to interface show. There we go. Okay, so the goal is the desired heading in radians, and then the angular displacement in radians to the starting position is delta. And then the remaining rotation. I guess that's the response. Is this goal? I mean, this is definitely the goal. I just don't know if this is the goal. This is the feedback, or if this is. I don't know if this is the feedback or if this is the. What do you call it? The result. This might be the result, though, just at the end of the remaining. Okay. So we're going to send ROS to send goal. Send goal, or action. Send goal. Turtle 1. Rotate absolute. Turtle sim action rotate absolute. Theta negative 1.57. Well, that'd be negative half pi, so that should be pointed straight down, right? Feedback. Hey, there we go. All right, I was right. It's straight down. All right, awesome. Feedback remaining. Okay, so remaining is the feedback, result is delta. Okay. Okay, so I had it backwards. So goal, result, feedback. Okay. So you should see the turtle rotating. All goals have a unique ID shown in the return message. You should also see the result, a field with the name delta, which is a displacement to the starting position. To see the goal, use feedback. That's just what we did. Summary actions are like services that allow you to execute long-running tasks, provide regular feedback, and are cancelable. A robot system would likely use actions for navigations. An action can tell a robot to travel to a position. While the robot navigates to the position, it can send updates along the way. And the final message once it's reached its destination. Turtle Sim has an action server, then action clients can send goals for rotating turtles. In this tutorial, you introspected that action, Turtle 1 rotate absolute, to get a better idea of how they work. Now you've covered all the core ROS2 concepts. And then the next we're going to look at how to view logs with RQT console. Okay. What happens if I run RQT console? well, I mean, it's a ROS2 run. Okay. So RQT console is a GUI tool that is to use to introspect log messages in ROS2. Typically, log messages show up in your terminal. With RQT console, you can collect those messages over time, view them closely in a more organized manner, filter them, save them, and even reload the saved files to introspect at a different time. That's cool. Nodes use logs to output messages concerning events and status in a variety of ways. Their content is usually informational for the sake of the user. You will need RQT console and TurtleSim. ROS run RQT console. RQT console. Alright, look at that. RQT console. It's doing nothing. RT will open. The first section of consoles where log messages from your system will display. The middle, you have the option to filter by severity level. Bottom sections for highlighting messages that include a string you input. Okay, you can add more filters to this section. Now we start TurtleSim. We'll start TurtleSim. Okay, cool. Message spawning turtle at starting TurtleSim. Cool. Now if we publish some stuff, kill tell op keyboard here. It's doing a thing. Oh no, oh no, I hit the wall. That's funny. Oh yeah, I hear my CPU fans spinning up. That's funny. Okay. Okay, let's see how the pie's doing. And it's done. Okay. So now we're gonna, because we installed kernel modules, right? Sudo reboot. Okay. All right, and we'll come back to that later. Okay, RQT console. There's a lot of annoyance. It was mad at me for running into the wall. Setting the default logger level. TurtleSim node ROS args. And that'll let me set the only see warnings by default and not info. Now you won't see initial info when you start. That's because okay, cool. Launching nodes. Use a command line tool to launch multiple nodes at once. Ooh, open a new. We're gonna write our first something or another. All right. So I'll close RQT console. Okay, I probably don't have Vim. Okay, app install Vim. Apt update. Apt install Vim. These are meant to run stuff. They're not meant to be interactive shells, right? Sorry, they're not meant to be interactive containers. It's purely for the purpose of deploying software for it to run on top of. You're not actually supposed to, not really supposed to log into one of these containers. I'm signing off by. Okay, all right. Alrighty. So we're gonna don't forget to do ROS2 workspace. ROS2 launch TurtleSim multisim.launch.py. Oh, look at that. There's two simulators. This will run the following launch file. From launch, import launch description, import launch ROS.actions. Generate launch description, namespace TurtleSim1, package TurtleSim, executable TurtleSim node, output screen. TurtleSim2, TurtleSim node. Okay. The launch files are in Python, but you can also use XML and YAML to create launch files. You can see this will start two TurtleSim nodes. You can control TurtleSim nodes by publishing this over here. One of them should move, the other one didn't. And if we did the other one, now we can do that one. That one will move and the other one won't. Perfect. All right. So running these, it does a thing. The significance of what you've done is you with one command. Once you learn to write your own launch files, you'll be able to run multiple nodes and set up their configuration in a similar way with launch 2. So this is probably what launch files in Lino Robot meant. When it was talking about if you're planning to build your own custom ROS2 robot and using accessible parts, package contains launch. This repository contains launch files to easily integrate your do-it-yourself robot with Nav2 in the simulation pipeline. Okay, cool. So that's what a launch file is. Yay. All right. I wonder what the implication of the namespaces thing is, though. Alright, so in the next tutorial, recording and playing back data, you'll learn about another helpful tool, ROS2 bag. Oh, this will probably be interesting. Okay, ROS2 bag is a command line tool for recording data published on topics and services in your ROS2 system. And before ROS2 system, it accumulates the data passed on any number of topics and services and then saves it in a database. You can then replay the data to reproduce the results of your tests and experiments. Recording topics is also a great way to share your work and allow others to recreate it. You should have ROS2 bag installed as part of your regular ROS2 setup. So we bring back up our turtle sim again. Like ice turtle. Okay, and then we want to run teleop key. Wait, that's ROS run. What ROS? Oh, it's just it. Okay, it's the terminal goobered. Okay, so do that. Make dir bag files. Oh. Alright, change bag files, ROS2 topic list. Turtle 1 pose. Ooh, topic echo. So if we do ROS topic echo, turtle 1, command velocity, and then we do we can control our turtle, like always. But we can do ROS2 bag record turtle 1 command velocity. Now, if we control the turtle, it records everything that we send it. Writing remaining cache, messages. Ooh, ROS2 bag. Ooh, interesting. Run the command. Now, if we... It can also record multiple topics. We can do ROS2 bag info, ROS bag. So turtle 1 command velocity, type twist, serialization format CDR. Okay, playing topic. Ooh. ROS2 bag, play ROS bag. And it's moving on its own, but it runs into the wall because the command input is different. But because it's publishing stuff, we can actually still just come back over to our teleop keyboard and control it. And I'm going to diverge from the tutorial just a little bit. So if we can actually do this, and it's controlling the turtle. Okay, sweet. Let's actually copy one of these ROS bags over to our Pi and see if we can play it from another machine. So if we go back over to our Pi, because we rebooted it, right? We should come back up. There we go. Now we need to do source, opt, ROS, jazzy, setup.bash, right? What if we do ROS2 topic list? Okay. It's not discovering my desktop here. That's fine. env, print env. ROS2 automatic discovery range. Maybe there's a way of interesting. Well, this is using host networking, right? That's what the whole point, right? Docker, yeah, we're using network host, IPC host. So, I mean, Docker 0 is still a thing, but if we were to say apt update and apt install, not iperf utils, it's inet utils. What am I doing? Inet utils, right? Apt install. Oh, is it inet utils 2? No. Okay, where does the IP adder come from? IP adder command links. Package. Oh, IP route 2. IP route 2. Alright. Should be. I mean, we'll get everything on the host, but interesting. Yeah, why can I not do ROS2 topic list? Yeah. Was it ROS2 discovery server? Sometimes things don't quite work correctly. Jazzy. Fast DDS discovery server ID 0. What if we did this over here? Okay. And then export ROS discovery server equals 10.00.10 1811.811. Okay, ROS2 topic list. God damn it. All right. I mean, pinging me. Okay, maybe I need. Okay. Nope, that did not work. Okay. Hold on. Oh, hey, wait a second. It showed up. It did. Okay, ROS2 run turtle sim turtle teleop key. And we're controlling the turtle from the Raspberry Pi. Okay, cool. Yeah, so why did it actually take the discovery server? Topic list. Nah, I mean, ROS2 node list. Tall turtle. Okay, yeah. Tell turtle. I mean, interesting. Okay, cool. So if we send the ROS bag over to the Raspberry Pi, so if we do tutorial scp or well, rsync bag files to to stinger.local. We do go back over to our turtle sim thing. Where's our I need my hold on. I need my there we go. Stinger ROS2 or bag files. ROS2 bag info ROS2 bag. Okay, and then if we do ROS2 bag play ROS bag. And it starts running. Hey. So yeah, we're controlling nodes on my desktop from the Raspberry Pi. All right, cool. We just had to turn on one of these discovery servers because it was having trouble with the Wi-Fi broadcast domains. But either way, that's a topic for another day. Unset ROS discovery. Yeah, let's actually restart things. Okay. Yeah, let's see. ROS tell turtle node. Let's see what happens if we play it again. Oh, discovery server doesn't work. Yeah, it does actually. Okay. Nice. Cool. So we installed ROS on the Raspberry Pi, and clearly it works because we were able to send commands over to my desktop. And we played our bag back, and we listened to stuff. Okay, managing service data. ROS2 run demo nodes. You've been recording data between... Okay, you will be recording data between introspection client and introspection service, then display and replay that same data later on to record service data. Service introspection must be enabled on the node. Let's start with introspection client. Service echo, record services. Record all services. Spec service data. That's fine. Echo. Next steps. Okay. We finished CLI tools tutorial. We won't probably... okay. CLI tools tutorial. Now beginning client libraries. Using Colcon to build packages. All right. So, probably going to be able to close Turtle Sim now. Clear. Okay. And we'll just minimize the Raspberry Pi here. Background, prerequisites, install Colcon, install ROS2. So let's see if we have Colcon. We do, okay. Because we're running the full container package. ROS2, build a ROS2 workspace with Colcon, beginner. This is a brief tutorial on how to create and build a ROS2 workspace with Colcon. It's a practical tutorial and not designed to replace the core documentation. Colcon is an iteration of the ROS build tools, catkin, all it meant, all that stuff from ROS1 or earlier ROS. For more information on the design of Colcon, see this document. Oh dear. Okay. So install colcon. I mean, we've already got colcon. Apt install Python free colcon common extensions. Probably already installed. Yeah. Okay. Oh, hi, Peppy. The kitties are trying to play. Hello. Please don't eat my cables. Eating my cables is not cool. Come on. Get out from under there. I know. I know. Okay. So, we've got... Okay, so install ROS2, we already did that. A ROS workspace is a directory of a particular structure. Commonly, there is a source subdirectory. Inside that subdirectory is where the source code of ROS packages will be located. Typically, the directory starts otherwise empty. What does Lino Robot look like? Anyway, using colcon. Okay, compared to Catkin, there is no development directory. So create a directory, ROS2 workspace, to contain our workspace. We already have ROS2 workspace, so we're going to make a source directory in here. We're going to remove those bag files. Okay, so we have a source directory. At this point, we have a single empty directory source. Let's add some example sources. All right. We probably don't have Git installed. We do have Git installed. Okay, it's probably got enough to build software, but okay. So we're gonna check out. We're gonna git clone ROS2 examples to source/examples and using the Jazzy branch. All right, we did that. So if we do find source, there's a lot of stuff. Sourcing and underlay. It is important that we have sourced the environment for the existing ROS2 installation that will provide our workspace with the necessary build dependencies for the example packages. This is achieved by sourcing the setup script provided by a binary installation or source installation, i.e. Another colcon workspace, C installation. We call this an underlay. Hey, kitten. What are you doing? Yeah. What are you doing, babies? Yeah. All right. So, building the workspace. We're not using Windows, so we don't have to worry about that. In the root of the workspace, run colcon build. Since build types such as amend, CMake do not support the concept of development space and require the package to be installed, colcon supports the option symlink install. This allows for installed files to be changed by changing the files in the source space for faster iteration. Okay, so we're going to do colcon build symlink install. Interesting. All right, it built stuff. If we do colcon test, it'll run tests. Okay. All right. Still running tests. Launch test examples. Still running. How much power is that using? Not too much. It's fine. Probably get rid of some of these terminal windows here. Here. All right. That's the Raspberry Pi, so we'll leave that up. All right. Also kind of wonder how fast that would run on the Pi for kind of just a loose example, right? We compiled these examples. Oh, wait, hold on. Colcon build. It took 13 seconds on my desktop, and I don't know how parallel it was on my desktop, but if we make a ROS2 workspace, and we do git install, not git install, Jesus. Do we have git? Git's already installed. We probably have build essential already. Anyway, clone that, and we'll do colcon build, just to see how long this might take. I really wonder. Hit 0 of 22 complete. This might take a while. Yeah, it took 13 seconds on my 16-core Zen 4, 7950X. Let's see what it takes on a 2.5 gigahertz, quad-core Cortex A76. Yeah. We'll assume it's going to be quite a bit longer. We'll leave that running out of just pure curiosity's sake. All right, colcon test. Source the initial environment. Okay. So now we can do source install setup.bash. Oh, I spelled source wrong. All right. Now we can open up another terminal and rerun our Docker installation here. All right. Now we go to ROS2 workspace. We're going to source install setup.bash. And then let's run a subscriber node. So let's run the subscriber in here. All right. And then in another terminal, we can run the publisher. And stuff happens. Nice. Okay. Perfect. Create your own package. Colcon uses the package.xml. Oh no, XML. XML is not meant to be written by humans. Defined in our ROS enhancement proposal 149. Colcon supports multiple build types. The recommended build types are Ament CMake and Ament Python. What the heck is Ament CMake? I know what CMake is. What the heck is Ament CMake? Oh, it's meta CMake. Okay, meta. Hey, kitten, what are you doing? Grab a kitten. I grabbed myself a kitten. Here, gotta get your kitten to work on your robot projects, huh? Yeah. No, don't be so squiggly. I'm squirrely. Oh, I know. Do you want to play? Huh? Yeah, I know you went down, but I want to hold you. Soft kitten. Soft kitten. Okay, I'll let you down. Woo! Alright. Scuttles off as quick as she can. Hi, I'll give you attention too if you want it. Yeah. There's two of them. Yeah, you see the little kittens. Alright. So, create your own package. So, we can do... Colcon uses package.xml specific. Colcon supports build type. An example of a Ament Python build is the Ament index Python package, where setup.py is the primary entry point for building. A package such as demo node CPP uses the Ament CMake build type, as it uses CMake as the build tool. For your convenience, you can use the tool ROS package create to create a new package based on a template. Full description of creating a package and how to use ROS2 package create is in the upcoming tutorial, Create a Package. For catkin users, is equivalent of catkin create package, but catkin's old. So you set up colcon cd. The command colcon cd allows you to quickly change the current working directory of your shell to the directory of a package. As an example, cd some ROS package will quickly bring you to the package, some ROS package. To set up cd, you need to run the following commands to modify your startup script. All right, well, let's just see what happens. Source, user share cd, functions cd.shell, and then export cd root equals opt ROS jazzy. And now cd should let us change to, say, examples rclcpp. rclcpp. Hey, dang it. Okay. That's just examples, isn't it? It's just... What? Okay, hold up. How is our Raspberry Pi build going? 4 minutes, 1 second. All right, so it took 13 seconds to build. Admittedly, I bet there's not even enough work for my desktop to stretch its legs all the way. But yeah, it took 4 minutes to build what it took 13 on the Raspberry Pi. What it took 13 seconds to build on my desktop. So it was 16 times longer. Best case. Okay. So, okay. Tests. Okay, packages select. On the way, tab complete supports command completion for bash and bash-like shells. The autocomplete package must be installed, and some setup might be required to make it work. If you do not want to build a specific package, then place an empty file named ignore in the directory, and it will not be indexed. If you want to avoid configuring and building tests and CMake packages, you can pass CMake args build testing 0. If you want to run a singular particular test from a package, you can do packages select ctest args, your tested package. Okay, set up mixins. Various command line options are tedious to write and or difficult to remember. For example, to change the CMake build type to debug, you normally use build CMake args. Okay, we could say no, do not eat my wires. Okay, to make common command line options easier, sorry, just observing the kitten. Hey, look at that. Woo. Go get it. Go get it. Go get it. Go get it. Hi. I've got a kitten. Look at this. She's not happy about this. Hi there, kitten. Yeah? Yeah? I'll let you down. You just don't. I don't want you to fall. Here, there you go. Okay. RAM limited. Well, it's an 8 gig Pi, so probably not. For example, to change the CMake build type to debug, you normally use build. Okay. Debug, mixin, add default. To install the default mixins, run the following. Repository default already exists, and then we could say build mixin debug. That's cool. And then what will that let us do for a release kind of thing as well? Yeah, okay. That's good. Okay, we can build with debug. For more details, see the mixin repository. Can you not? Hold on, just a second. Okay. Just a second, I need to save some wires. Okay. Kittens. No. No. Stop attacking this stuff. Hey, what are you up to? Alright, there you go. Alright. I think I've secured the wires. Alright. At least for now, anyway. Alright. So, local mix-in repository. What kind of build type mix-ins? Debug, release, rel with, all the stuff. Okay, cool. I see. No, go away. Sorry. For some reason that made my phone think I was trying to talk to it. Okay. Who is... Sorry. It's photos. Okay. Alright, mix-ins and such. Okay, creating a workspace. Creating a workspace and learn how to set up an overlay for development and testing. Alright, starting to get to the important stuff. Background, a workspace is a directory containing ROS2 packages. Before using ROS2, it's necessary to source your ROS2 installation, workspace, and the terminal you plan to work in. Hey. No. Okay. You also, sorry. A workspace is a directory containing ROS2 package. Using ROS2's source workspace makes ROS2 packages available to you. Okay. You also have the option of sourcing an overlay, a secondary workspace where you can add new packages without interfering with an existing ROS2 workspace that you're extending, or an underlay. Your underlay must contain the dependencies of all the packages in your overlay. Packages in your overlay will override packages in the underlay. It's also possible to have several layers of underlays and overlays, with each successive overlay using packages of its parent's underlays. Okay. So we already have a ROS2 environment. We have... we're going to remove all this stuff. ROS2 workspace, rm-ref star. All right. We're going to make a source directory. We're going to go to the source directory. Okay. Another best practice to put any packages in your workspace into the source directory. The code above creates a source directory inside of ROS workspace and navigates to it. Okay. Sure, you're still in the ROS place before you clone. We're going to get our ROS tutorials. I'm going to clone that in here. Now the ROS tutorials is cloned into your workspace. ROS tutorials contains a turtle sim package, which we'll use in the rest of the tutorial. The other packages in this repository are not built because they contain a colcon ignore. Okay. Find dot dash name colcon ignore. I don't see a colcon ignore. Either way. Resolve dependencies. Okay, so Linux, if you're still in the source directory, if the role with ROS tutorials clone, make sure to run ... so we get back to the workspace. We can do rosdep install -i from path source ROS distro jazzy. Yes. Okay, deprecation warning package resources, deprecation as an API, see setup tools. From package resources, import load entry point, all ROS steps installed successfully. Perfect. Build the workspace with colcon, build. All right, I wonder what kind of computer they were using. All right. I wonder, colcon clean, is that a thing? Is that a thing? How do we colcon clean? Where's the build directory? Is that, oh, there's literally a build directory. Okay. Install log. What if we did colcon build clean? I just want to see how parallel this actually is being. Clean, oh, colcon a build. Not particularly. How'd they finish in 5.8? Either way. Anywho. Alright, one useful argument. Packages up to... Builds the package you want plus all its dependencies, but not the whole workspace. Symlink install saves you from having to rebuild every time you tweak Python scripts. You know, that's probably a handy thing. Event handlers console direct plus shows console output while building, can otherwise be found in the log directory. Executor sequential processes packages one by one instead of using parallelism. Once the build is finished, enter the command in the workspace root, ROS workspace. You'll see that colcon has created new directories. Okay. Okay. What are they doing? Alright, so we've got our workspace. The install directory is where your workspace setup files are, which you can use to source your overlay. Sourcing the overlay before sourcing the overlay. It is very important that you open a new terminal separate from the one where you built the workspace. Sourcing an overlay in the same terminal where you built, or likewise building where an overlay is sourced, may create complex issues. In the new terminal, source your main as the underlay so you can build on top of it. Before sourcing the overlay, it's very important that you open a new terminal separate from the one where you built the workspace. Sourcing an overlay in the same terminal where you built, or likewise building where an overlay is sourced, may create complex issues. In the new terminal, source your main as the underlay. Go to the root of your workspace, source your overlay. Okay, well, we'll do that in this one. Go to ROS2 workspace. We already get the main one sourced by our ROS entry point. So we'll then source install local setup.bash. Okay. Sourcing local setup of the overlay will only add packages available in the overlay to your environment. Setup sources the overlay as well as the underlay it was created in, allowing you to utilize both workspaces. So sourcing your main ROS installation setup, and then the ROS workspace's overlays local setup, just like you did, is the same as sourcing ROS2 workspace's setup, because that includes the environment of its underlay. Now you can run the ROS2 package from the overlay. Okay. Turtle sim node, perfect. And let's see that it's actually using the right executable. Yeah, ROS2 workspace install turtle simlet. Okay, sweet. We're using the one that we built from source. Okay. Hold on just a second. Y'all doing? You'll lose your toy? Hey. So, TurtleSim node, modifying the overlay. You can run TurtleSim in your overlay by editing the title bar on the TurtleSim window. Okay. So, we're going to go into, because we built it in here, we'll rename it to My TurtleSim, and that's in turtleframe.cpp. So find name turtleframe.cpp. Okay, hold on. Vim. We don't have Vim because this is a Docker container. Oh god, guys, stop. Please. It's gonna make a loud noise if you keep messing with it. If you knock it over, it's gonna be loud. That's fun. Okay. Jeez. Okay. So we're now going to edit this. We're going to do, where is the title? TurtleSim. There we go. I'm going to change this to My TurtleSim for Sheldon. Okay, and now we're going to do colcon build. If you run the TurtleSim node again, it should say My TurtleSim for Sheldon. Okay, so we changed it. Perfect. See that modifications in the overlay did not affect anything in the under. Ah, yes. And then if we go over here, ROS2 run TurtleSim node, right? Right, and this is the original TurtleSim because we have not sourced our workspace. Okay, okay, I get it. That's neat. So, overlay, underlay. All right. So I guess the main question is okay, if we've got our terminal sourcing the ROS2 workspace, do we need to not have it that way? Like, or if we source one of these local environments, will that override the fact that we sourced our installation workspace? I guess we'll find out in the future, I guess. Okay, now we're going to get to creating a package. I think this will be the last little tutorial bit that we do for the night, just because I need to get off at 9-ish, just because I'm going to Maker Faire tomorrow. Okay, so all right, ROS2 package. Package is an organizational unit for your ROS2 code. If you want to be able to install your code or share it with others, then you'll need it organized into a package. With packages, you can release your ROS2 work, and others will be able to build and use it easily. All right, I see. We're just going to finish this one. You know, it's only the rest of this page. It's fine. It'll take like 5-10 minutes. Then it'll be time to get off. Packages in a workspace. A single workspace can contain as many packages as you want, each in their own folder. You can have packages of different build types in one workspace. You make Python whatever. You cannot have nested packages. No, do not eat the wires. No. Stop. No. No. Come back here. You little carpet shark. Here we go. All right. She likes to eat wires when I'm not paying attention to her. Hi. Okay. All right, there you go. Wow. Okay, so package and workspace can contain as many packages as you want, each in their own folder, no nested. Trivial workspace might look like the following. Prereqs, source your ROS2 installation, which we did. Then we're going to create a package, and we're going to call it my no, or we're going to call it node name, my node, my package. All right, creating my package, include my package, node name, my node. Okay, we created the thing, turning the command, your terminal will return all this stuff. Building a package, we can do colcon build. And we built my package internal sim, all right. And then if we should be able to say ROS2 run my package, my node. Ah, that didn't work. If we resource this, ROS2 workspace, source. Oh dear, hold on. Did I do this in the wrong directory? Oh yes, yes I did. Okay, we're going to remove my package. Supposed to go to the in here and then create our package and do our colcon build. All right, build install log colcon build. All right. All right, and if we source install / local setup.bash, we should be able to do that. Oh yeah, ROS to run my package, my node. There we go. Hello world, my package. All right. We can also specifically select to only build our package, which we built. Then we install the thing, use the package, run the node, hello world package, examine package contents, ls source / my package, source my node. Hey, printf, hello world my package. You may customize package.xml. You may have noticed the return message, the field's description and license contained to do. Source my package. Oh, Jesus Christ. There's probably no nano as well. Nope. All right. Well, we'll do it from up here because we bothered to install them. All right. Yeah, to do package description, license maintainer, all this fun stuff. Don't forget to save once you're done editing. You're all done. All right. Oh, we could have done this in Python as well as C++. Interesting. Okay. Contains the same description. It'll auto-generate that thing. Don't forget to save. All right. So, running a simple publisher and subscriber. We will do this next time because it is time for bed because I have to go to Maker Faire tomorrow. All right. So, we will leave off here for tonight. And we'll pick up with this publisher subscriber thing in the next stream, which maybe we'll do next week. There's also a concert next week. Either way, maybe next week. But I will write a post on the YouTube page if I am going to be doing one. And then actually, hopefully, we'll get into writing some ROS code that'll run on the Pi, that'll do something, or run on a robot that'll do something specific for our robot. But next stream, we'll continue going through these tutorials, and then maybe, hopefully, we'll get to using doing some microcontroller work with micro ROS, so that we can actually start doing stuff with the robot. The micro ROS would be to actually have the microcontroller code doing something, and then we'd run full ROS stuff on top of it. But either way, so thank you everyone for watching, and sticking around. It was not the most entertaining thing going through tutorials, but this is my first time using ROS in a long time, so I needed to go through them. And I was trying to promise that I do things for this only on stream. I don't want to do too much off stream, just so that you can kind of have a realistic idea of how long it takes to do these things. If I have a camera pointed at myself the entire time, I have a documented record on how long it took me to figure something out. So, so again, thank y'all for watching. If I'm going to do a stream next week, I'll post a thing on the YouTube page. But other than that, hopefully see y'all next time.